Hello again. I'm going to talk to you today about phase diagrams and how we would be able to compute the phase diagrams from thermodynamic data. The idea is that we want to study equilibrium between several elements in an alloy and determine the concentrations of these elements in the liquid phase and the solid phase and the vapor phase if needed. So it's a very general method that we will use. However, we're going to apply it just for the case of solid-liquid equilibrium, and I'm going to give a specific example on how to apply this for the case of copper and gold, for example, and compute the concentrations in the liquid and in the different phases that will come out. So the title today is phase diagrams, and in phase diagrams we will study the conditions for equilibrium. So let's see if we remember from the previous lectures. Is the basic idea is that if I want to compute the chemical potential, then the chemical potential will be a function of the Gibbs free energy of the element in the unmixed pure state, and then we have a part that comes from mixing, and then we decided that we would have these equations for the chemical potential as follows. So if we have, let's say, two elements only, A and B, then the chemical potential of element A and B will look like this. So in this case, I'll have mu of element B is equal to G plus the concentration of element A times dG by dxB. Remember that we have now two concentrations, and the two concentrations or the two elements will exist in the two phases. So let me just summarize. We have element A and element B, and we have phase alpha and phase beta. These are the different things that we have to consider here. So the equation that you see on the board is the chemical potential of element B in the solution, and it has G of the particular phase. So we have a function of Gibbs free energy of the two elements together, and then you have the concentration of A times dG by dxB. Similarly, I can write an equation for the chemical potential of the element A, and that would look like this situation. So let me remove myself here to give more space, and then I have here mu of element A will be also equal to G, whatever G is in G of the of phase alpha or phase beta, so it'll be G plus x sub B times dG by dxa. Generally, we would like to study the concentrate everything in terms of one concentration. So we note that there is a relationship, like we note that there is a relationship between the two concentrations of the two elements, that XA plus XB is always equal to 1. And we will use this so that we can focus on the dependencies. All the dependencies will be in relationship to XB, for example. And we can retrieve every dependency for element A from just the fact that XA is equal to 1 minus XB. So we'll do that in here. So if we just continue on here to have in the next page here, note that XB is equal to 1 minus XA. So we know that. and therefore d by dxb, if I want to take the derivative with respect to a, for example, will be minus d by dxb, and therefore I have now two previous equations. I can write them in this form. So I have mu b is equal to g minus plus 1 minus xb times dg by dxb, and this is evaluated at a particular concentration of b. We're going to call it xb0, and then similarly I have mu of element a as g minus now x sub b times dg by dxb at the same concentration of b in x and in 0. So you look at these two equations. So let me just kind of let you have a look at them, and then I'll talk about them. We have, as you can see now, I have two equations, one for the chemical potential of element A and one for the chemical potential of element B. And these two equations have to be written for phase alpha and for phase beta. And I'm writing them as all of the dependencies now in terms of x sub b. So that's the situation here, because once we find the equilibrium concentration x sub b in the alpha phase and x sub b in the beta phase, then we're able to find the corresponding x sub a. So let's write down the equilibrium conditions. Equilibrium conditions is that we would equate the chemical potentials in each case. All right, so before I do that, I want to discuss the graphical meaning of each one of these equations. So the graphical meaning is that I'm going to discuss this in the form of a graph. So if I just, let's say, develop a graph like here for the Gibbs energy as a function of the concentration of an element. So if I take on this axis here x sub b going from 0 to 1, and I take on this axis here g going up here, and then represent the Gibbs energy, for example, for any phase. So this is the Gibbs energy for any phase, G, here. And I'm interested in what happens here at a particular fixed concentration, x sub b 0. And I wanted to determine the chemical potentials. So if you see the previous equations, you see that the chemical potential is basically the slope of this line here. It plays a role in the following sense. So if I look now at the value that I have here, this value is the value of G, and then if you go to this side here, then you have this amount is equal to 1 minus xb times the slope, and the slope is dg by dxb, and the slope is evaluated at xb0. And this amount on this left here is equal to minus x sub b, and times the slope again dg by dxb on the side, because from here to here is xb, and then you take the slope. So it turns out to be, if you look graphically, the height from this point all the way to the bottom here is mu and mu sub b, and the height from this level to the 0 is mu sub a. So the mu is basically the intercept of the slope on both axes. So as you can see, the concept that we're trying to develop graphically is a reflection of any one of these two equations. The equation tells us that mu is equal to g plus a little bit or minus a little bit. If it is on the b side, which x sub b equals 1, then it will be plus the distance, which is 1 minus x sub b, times the slope, dg by dx sub b. If it is on the a side, then it will be the g, value g, minus the distance, which is x sub b, times the slope again. So in this case, we see that all what we need to do, if we just plot the g curve, take the slope of the g curve, the intercept on the right side will be the chemical potential of element B. The intercept on the left-hand side will be the chemical potential of the element A. Now you can ask yourself, what happens if I have now two phases? What I showed here is just for one single phase. What happens if I have two phases in equilibrium? How do I compute the concentration of element B in the alpha phase and in the beta phase? In other words, I'm looking for two numbers. What is x sub b in the alpha phase, and what is x sub b in the beta phase? That would make the slopes to be equal, which means that, or it makes the intercepts to be equal. And this is obtained graphically in the following way that I'm going to show you here for two phases and two elements in them. So let's just go here and go to the next page, and now try to make a graph that has that story for two phases and two elements in the two phases. So if I have here, this is the same idea in which I have now on this side I have x sub b, and on this side I have a representation of g, but I now have two curves. So one for the liquid, let's say, and then the other one would be for the solid. So let's say that the solid is another one. Let's say I'm going to just take a slope first to assist me in making the graph neater. So if I take a slope here, and just let me remove this. I take a slope. Yeah. So I have a slope here for that gives me a solution for the liquid, and then I'm going to represent the solid. Let's say it has to have a matching slope right like this. So in this case, this will be g of what happened here? Okay, so we're back here. So all right, so I'm going to just do it again. So if I do it again, I have here, so this free energy is for beta, and this free energy is for alpha. And the points that in which you have equal slope, let's say that you have one here and one here. These 2 points I'm going to call an x, b, 0 in the beta phase, and this is x, b, 0 in the alpha phase. I can remove the 0 and just xb in the alpha and xb in the beta, And by now, from the construction, graphical construction that we had before, we can make certain that the intercept on this side is mu of element B in the alpha phase, and that is also equal to mu of element B in the alpha phase. Both of them are evaluated at x sub B, in this will be evaluated at the alpha phase. Let me take that back. This is in the beta phase, and this is actually in the beta phase. And this will be evaluated at x sub B in the alpha phase. On that side here, the intercepts will be two identical intercepts. One of them is mu for element A in the beta phase, evaluated at x sub B in the beta phase. And the other one is mu sub B, sub A again, sorry, in the alpha phase. So this is mu sub A. Just be clear here. So this mu sub A is the same element, but now it's in the alpha phase, but it is evaluated at x sub B in the alpha phase. So that's how we're going to write it down. And therefore, we find the common slope, and we are just done with this process. Now, if I don't want to do common slope, then I need to do something else. I need to solve it analytically. And here's the procedure that I'm going to show you to solve it analytically. So if I want to solve it analytically, I have here to write the two equilibrium equations. So I have equilibrium, and the equilibrium, now I'm going to write it for element A and element B. So element A will be equation 1, mu of element A in the alpha phase, and this is evaluated at x sub B in the alpha phase, equals to mu, the same element, in the beta phase, and this is evaluated at x sub B in the beta phase. Equation 2, mu of element B in the alpha phase, evaluated at x sub B in the alpha phase, is equal to mu sub B in the beta phase, evaluated at x sub B in the beta phase. So these are two equations in two unknowns. And what are the unknowns here? The unknowns are, so let me just kind of pull myself to the side here to write the unknowns. So the unknowns are x sub B in the alpha phase and x sub B in the beta phase. So these are two unknowns that we are looking for. Once we find them, of course, we can find x sub A in the alpha phase and x sub A in the beta phase, because we know that these are the complements of the x sub B in alpha and the beta phase respectively. And these two equations are nonlinear equations. So equation 1 and 2 are nonlinear. And we solve by iterations. So it's either that we have the common tangent approach, or we have to solve the problem by iterations in the system. So let me just now, okay, I have this. This is the procedure that we have for two species. Graphically, we would just use the common slope for the free energy in the alpha and the beta phase, and the intercepts on the left and right will give me the solution, and the concentrations will be those determined to be at the common tangent. In case we have to do it numerically, we just set up two equations and two unknowns, and the two equations are for the chemical potential of each element separately in the alpha and the beta phase separately. And chemical potential has the Gibbs free energy, and it has also the gradient of the Gibbs free energy. So these will be functions of the concentrations, and then we would have to solve these simultaneously together. So this, I think we have a pretty good idea about how to calculate the phase diagram from the Gibbs free energy. And what I wanted to do now is that suppose that we have the phase diagram, and we want to understand how the concentrations kind of split in different phases. So let me just talk about an example in which we develop what is known as the phase rule, which tells us about the ratio of the concentration of the phases if we know the phase diagram. In other words, it's the inverse process. Here we're constructing the phase diagram from the Gibbs free energy, and then the next process is going to be, given that I have the phase diagram, how can I calculate the concentrations at equilibrium? Of course, this will be a lot easier than doing the procedure that we did to construct the phase diagram in the first place. So let's discuss that in a minute here. So next is going to be this topic that we will discuss is the topic of the phase rule. So in the phase rule, I have now, let me write it down here in big letters. So we know that the objective here is to actually develop an understanding of how to calculate the concentration of the phase diagram. So let's see that I have a piece of the phase diagram that looks like this, and this is the temperature versus the concentration X, and this concentration is X sub B, because we have two elements, let's say, and we have the concentration X of one of them. And on this phase diagram, on this plot between T and X, I have now phase boundaries. So I have a boundary like this, and I have a boundary like that. And then on these boundaries, I have an alpha phase on this side, and I have a beta phase on this side, and in between I have an alpha and a beta phase to coexist. Now let's say that I constructed what I call an isotherm, which is what's sometimes called the tie line. So this is an isotherm or a tie line or tie line. And suppose that I am actually cooling an alloy from high temperature, like here, and I'm cooling it down. And then I'm looking for what happens to the concentrations at this temperature T sub 0. So at T sub 0, I have now the state is denoted by this dot. I have an initial concentration of X is X sub 0. Let's call it X sub 0. And the concentration at the phase boundary, we're going to call it X sub alpha. And the concentration at this phase boundary, we're going to call it X sub beta. Now let's say that we have a total number of moles is N total. And N total is going to be split either in between the alpha and beta phase or distributed amongst the concentrations. So if it is between the alpha and the beta phase, it will be N is equal to N sub alpha plus N sub beta. These are the two molar number of moles in the alpha and the beta phase. And we also, if we want to look at the amount of the element that we are interested in, xb now, the total amount is fixed, which is x sub 0 times n. So this is the total amount at the beginning of the solidification process here, or at the cooling process. So the total amount is x sub 0 n, and this total amount is going to split. Part of it is going to be in the alpha phase, and part of it will be in the beta phase. So we will have basically two equations that we can solve to find the two unknowns that we have, and two unknowns is x sub alpha and x sub beta. So given x0, what is this and what is that? So let me now go to a clean page and start writing it down. So here I have equation 1 is n is equal to n sub alpha plus n sub beta, and equation 2 is x sub 0 times n is equal to x sub alpha n sub alpha plus x sub beta n sub beta. And note that this is a very interesting analogy to mechanics, because if I look at these two equations, I have a tie line like this, and the tie line has on the two ends of the tie line, this is here, the concentration is x sub alpha, and I started here at x0, and at on the other end is x sub beta. And I can now, to make an analogy to mechanics, complete analogy to mechanics, I'm going to say that the number of moles here are like forces. So I have a force N here, and now the force is split into an N beta and N alpha. So in mechanics, we know that if N is the sum of these two forces, so this is equation 1, like the sum of forces, this is equilibrium actually. I should reverse the arrow to make it consistent with mechanics. So let me just make this to the other side. So if I make the arrow here, this is N. So N is equilibrating N alpha and N beta. And the second equation tells me that if x's are distances, so if we just measure the distance from a 0 here, this is x alpha, this is x0, this is x beta, then I'm taking the moments of n on the left side, n times x0 is equal to the sum of the moments, which is x alpha and alpha, the moment of this force here, plus x beta and beta, which is the moment of this force here. In other words, it is the same idea of the moments, and we can determine x alpha and x beta just from the fact that we have moment equilibrium. So with that, we know now that the ratio from it is like basically equilibrium of a teeter-totter. So the teeter-totter is right here. This is teeter-totter, and then the fulcrum is at n, and then you have the two forces on both ends, n alpha and n beta. So n alpha times this distance should be equal to n beta times this distance. It's as simple as that. So with this, we can now write equations for the fractions. So equations for the fractions, we can have n alpha over n is equal to x beta minus x0 divided by x beta minus x alpha. So, and then also n beta over n is equal to x alpha minus x0 divided by x beta minus x alpha. And note that everything here is in molar fractions. So we have to be careful that all of the quantities that enter here are in molar fractions. So let's just go back here to make reference. If you look at this equation, n times x beta minus x0 will give us n times x beta minus x0. You're taking the moment of n about that end is equal to n alpha times the x beta minus x alpha. In other words, you just take the moment about this end first. If you take the moment about this end first and then take the moment about this end first, you will get the two equations here that determine the concentrations. So next is that, okay, so we're all done, because if we have the phase boundaries, we can represent them by straight lines, and we know the initial concentration x0. We take the moments about one side or the other, then we can find the corresponding concentration in phase alpha and phase beta. Notice that I'm talking about all of this is dependent on one of the concentrations, the x sub b, for example. One of the issues is that the phase diagrams are usually given in terms of weight fractions. So, and all of the chemistry, thermochemistry that we use are in the thermochemical derivations and quantities that we have are in terms of the molar quantities and molar fractions. So I would like to spend just a few minutes to show you how we would convert from weight fractions to molar fractions, so we can actually do the changes from the actual phase diagram to the corresponding concentrations for a given temperature. So let's do that here. So I will write now that we have given now we have mass fractions or weight fractions, and the weight fractions I'm going to denote these by Z, and molar I'm going to denote this by X. So if I have let us have a mass M, so we have a mass M, and molar masses M sub A and M sub B, then we can write X sub A is the ratio of N sub A divided by N sub A plus N sub B. And N sub A is the Z, this is the weight fraction of element A times its mass, so this is the mass fraction if I divide it by M sub A, which is the molar mass. And this will be ZA times M over MA plus ZB times M over MB. And therefore, I have now an equation that relates X sub A to the mass or weight, the weight fractions, ZA MB divided by ZA MB plus 1 minus ZA times MA. And this equation can relate the weight fractions to the mass fractions that we can use right away. So with this, I think we have with this part we have now a complete determination of we can convert the weight fractions that we get from the phase diagrams to corresponding molar fractions that we use actually in our equations for the moments that I discussed on the tie line, and therefore we can get the corresponding concentrations for any given temperature. And with that, I think we're going to stop the lecture.